I'd like to start today's class by looking at the example in the textbook 6.5 of a person riding a Ferris wheel. Now in this example they looked at the forces that act on the person at the top of the arc and at the very bottom of the arc, or the top of the circle and the bottom of the circle. I'd like to look at the forces that are acting on the person when they're halfway between the top and the bottom. So in this example, we have our person sitting in our chair, and the first force we can think of acting on this person is the normal force from the chair. It pushes upward on the person. And you can see now that the normal force from the bottom of the chair, the seat, is not pointing in the radial direction, so it is not a radial force, not centripetal. We also have the weight force, which always points downward. Again, we see that this force does not point along the radial direction, so it is no longer a centripetal force. There is a centripetal force, however, or the person wouldn't be going in a circular path, and this is another normal force. The seat back from the chair pushes inward towards the center of the circle. And so it is this orange vector, the normal force from the back, that is our radial force. So let's apply Newton's second law in the radial direction. Sum of centripetal forces is mass times centripetal acceleration, or the normal force from the back equals mv squared over r. In the example, they tell us that the Ferris wheel is rotating at a constant rate such that the person has a speed of 3 meters per second and the radius of the Ferris wheel is 10 meters. So we can put those numbers in. And I'm going to multiply and divide by g here, much like they did in the example, because they found the normal force in terms of its percentage of the person's weight. So when we do that, we find that the normal force from the back is about 1/10 of the person's weight. So while in the textbook example, the upward normal force and the downward weight force were both radial forces, at this point, they are not. Let's consider a different example. Imagine that you have a yo-yo, say, on the end of a string, and you're going to rotate that in a vertical circle. So it goes up and down in a vertical circle at constant speed. The force of the string on the yo-yo is a radial force, and that's the tension that I've drawn here. And there's also a weight force that acts on the object, and you can see that that is pointing in that direction. They're both radial forces because they point along the line of the radius, but one of them is positive and one of them is negative. Let's assume that the yo-yo has a mass of 1/2 kilogram, that the length of the string is 0.3 meters, and that you rotate this such that the yo-yo has a constant speed of 4 meters per second. Let's apply Newton's second law of motion to the yo-yo at this point and find the tension in the string. So here we have tension minus weight equals mv squared over r. Because they point in opposite directions, one is positive, one is negative. So tension equals weight plus mv squared over r. So in this case, our tension is 31.6 newtons. Now let's look at the yo-yo when it's halfway to the top. There's a tension force, which again is still centripetal or radial. It points along the radial direction. But now the weight force is not a centripetal force. Applying Newton's second law of motion, we get that the tangential force is 26.7 newtons. Now let's look at the yo-yo at the top of its swing. It still has a speed of 4 meters per second. There's still a tension force which points to the center of the circle like it has the whole time. But now the weight force also points to the center of the circle. Tension and weight point in the same direction now, so they both have the same sign. Applying Newton's second law of motion, we see tension plus weight equals mv squared over r. And solving for tension, we get that tension is 21.8 newtons. So while the tension force in this example is always pointing towards the center of the circle, the weight force sometimes points away from the center, sometimes doesn't point along the radial direction at all, and sometimes points in towards the center of the circle. Well, let's consider a slightly different example, say with our yo-yo. Instead of rotating it in a complete circle, let's say we let it swing back and forth like a pendulum. And we will look at it at the very top of its swing, at its maximum angle there, theta. Well, at the very top of its swing, there are forces that act on it. There is a weight force, which always acts downward. But this weight force can be thought of as having two components. One that points along the radial direction, along the radius, and one that points tangential to the path. Now, this angle theta is also the angle indicated down here in the weight vector area. So I can write out the weight components, radial and tangential, as I've seen here. Now at the very top of the path, the speed of the pendulum is 0. It has no velocity in that very instant when it gets to the very top. And so the tension force in the string balances the radial component of the weight. They're exactly the same. And in that very instant, at the very top of the swing, when the speed is 0, and the tension balances the radial weight component, the centripetal acceleration is also 0. But the pendulum's not going to stay at that point. The tangential component of the weight is going to cause it to swing back down. Which means that there is a tangential acceleration. In other words, the object is going to speed up as it swings. So the speed is actually changing. Let's look at this pendulum at several locations along its path as it swings back down to its lowest point. At the very top of its path, we said the velocity was 0, and so the centripetal acceleration is 0. But it does have tangential acceleration, so its speed is going to increase. Now let's look at it at this point. It's swung a little bit. It still has tangential acceleration, although from our previous slide, we saw that that acceleration depended on theta. So a sub t is actually getting smaller with time, but the speed is increasing. So now it has some velocity, and so it has some centripetal acceleration. Let's look at it at this next point. Still has some tangential velocity, although tangential velocity is getting smaller and smaller. But because there's still tangential acceleration, the tangential velocity is getting bigger, so the speed is getting larger. And as speed gets larger, centripetal acceleration gets larger. At the very bottom of its path, the tangential acceleration has decreased to 0. That means the amount of speed that it gains with time has decreased to 0. And it's got its maximum speed at this point. That means it has its maximum centripetal acceleration at this point. The object has acceleration in the direction of its velocity because its speed is increasing with time. This is the type of acceleration we've been talking about all semester, speeding up. But it also has centripetal acceleration because the direction of that velocity is changing. But the new complication here is that the centripetal acceleration itself is changing its value because the speed is changing. This is an example of non-constant acceleration. That means the acceleration is accelerating. And this is the first example we've looked at this semester of an object that did not have a constant change in velocity or a constant acceleration. So let's work through a couple of examples. So I want to look at problem 6.3 out of the textbook. Problem 6.3 says, a car initially traveling eastward turns north by traveling in a circular path at a uniform speed as shown in this diagram. The length of the path from A to B to C is 235 meters, and the car completes the turn in 36 seconds. So first, we want to find the average speed of the car. So speed is just distance divided by time. You take the 235 meters of the path, divide by the 36 seconds, and you get 6.53 meters per second. Now we want to find the acceleration of the car. The acceleration of the car is centripetal. And centripetal acceleration is v squared over r. We know what the v is. We know the speed. We just found it. But now we need the radius of the path. Well, the distance that it travels is 1/4 of the circumference of a circle. So d is equal to 1/4 times 2 pi r. And we can solve for the radius then, which is 149.6 meters. Put that into our centripetal acceleration formula, and we get that centripetal acceleration is 0.29 meters per second squared. Lastly, we're asked to write that centripetal acceleration in its I hat, j hat vector form. So the centripetal acceleration points along the radius in this way. So we can draw in components that point in the x direction and the y direction. And this is negative because it points in the negative x direction. Now let's look at problem 6.9. And this says that a hawk flies in a circular path of radius 12 meters with a constant speed of 4 meters per second. And we're asked to find the centripetal acceleration. Well, it's v squared over r. So centripetal acceleration is 1.33 meters per second squared. And that points in towards the center of the circle. Part B now tells us that at some instant, the bird starts to increase its speed. So it now has tangential acceleration of 1.2 meters per second squared. And that, of course, points tangential to the circle. So at the instant it begins to speed up, its initial speed is 4 meters per second. And so its centripetal acceleration is the same as we just found. The problem asks us to find the total acceleration at that instant. So the total acceleration is the vector sum of a sub c plus a sub t. And since those are perpendicular to one another, the Pythagorean theorem gives us that total acceleration of 1.8 meters per second squared. And now we need the direction. So the total acceleration is 1.8 meters per second squared at 42 degrees to the radial direction. Now, that's not going to be constant because as the speed increases, as the bird goes from 4 meters per second to 4.2, 4.5, 5 meters per second, etc., the centripetal acceleration will increase in value, and that total acceleration will therefore change. So let's look at the speed of the bird at 3 seconds. If it gains speed at 1.2 meters per second for every second it travels, at 3 seconds its speed is 7.6 meters per second. And its centripetal acceleration at that point would then be 4.8 meters per second squared.